I'm Lachlan Carey. I'm a manager here at RMI in the US program where I work on economic development and industrial strategy. And I just want to welcome you all to our webinar on unlocking electro-industrial growth to meet surging electricity demand. A lot going on in that title. Hopefully, by the end of today's webinar, you have a better sense of each and every one of those terms. To start with a bit of an introduction to who will be joining us on the panel, to who we are, and what we're going to be going through today. So, for those who aren't familiar, RMI is an independent, non-partisan nonprofit that uses market-driven solutions to accelerate a prosperous, clean energy future for all. So today's session is a joint session between RMI and Rhodium Group, made possible by the New Energy Industrial Strategy Centre, or NEIS. This is a global network of researchers, policymakers, and private sector stakeholders advancing new energy industrial strategies. And we've been working on this since about July or August last year. And so this particular project is really thinking about this pivot to industrial policy that we're seeing nationally, that we're seeing globally, how that interacts with subnational and state policy, and the types of bottlenecks and demand pressures that we're seeing, particularly on the electric grid, is a big part of what we'll be going through today. We're working with the Rhodium Group as part of this project to model what happens when states deploy some of these industrial policies that we've seen at the national level, and walk you through some of those results. A quick bit of housekeeping before we get started. This session is being recorded, and the recording, along with the resources, will be posted on our event page within 24 hours. If you have any questions at any point, please drop them into the Q&A box, and we'll get to them at the end, where we've hopefully left enough time for sufficient Q&A. So, in terms of our agenda for the day, I'm going to do a brief bit of introductions. I'm then going to talk you through RMI's approach to electro-industrial economic development. We released a report late last year called Grease Lightning, where a lot of these findings are coming from. We'll then turn over to Rhodium, who's going to go through their modeling results for the Southeast. And as I say, finish with a bit of Q&A. So let me introduce today's speakers. I'm joined by three colleagues from Rhodium Group who led the economic modeling you'll hear about in the second half of the session. We have Ben King, who's director at the Rhodium Group and helps lead their energy and climate work, Galen Bauer, a senior associate, and Helen Colas, a senior associate also at the Rhodium Group. So I did want to start today with just a bit of scene setting. So what we like to say at RMI is that we bring the charts. So I am going to throw a bunch of charts and a bunch of graphics at you. These slides will be available after the webinar, so please feel free to go through at your own pace, or come and talk to us afterwards, and we'd be happy to talk more. So the big picture that we see is these three structural pivots that are reshaping the map. You have these changes in technology, in geography, and policy that together are ushering in what we sort of in a grandiose way are calling the electro-industrial era. So first is this technology pivot. Electrified, digitally controlled systems are converging into a single stack that scales like manufacturing, but improves like software. I'll talk a little bit more about what that means in a moment. The second is this geography pivot. Investment is concentrating in regions where we see power, prepared sites, workforce, and policy all aligning. And then finally is the policy pivot that I've already spoken to a little bit. Industrial policy has clearly returned as an active tool, not just here in the United States, but around the world. And governments are shaping markets to crowd in private capital and accelerate project delivery in these technologies that are increasingly important for economic development outcomes, to meet electricity demand, for national security and geopolitical outcomes, and of course for climate and clean energy outcomes as well. So first is this technological shift to what we call the electro-industrial stack. And there are three key features of what we mean by this. The first is efficiency. So quite frankly, electric machines are just more efficient. They avoid combustion losses and they deliver precise real-time control. So if you take an example like thermal batteries, they convert low-cost electricity into long-duration, high-temperature heat at 90 to 99% efficiency. And this really is a game changer in a lot of different ways, and it's why we really see more and more of the investment sort of focus and direction and technological shifts heading in this direction. Second is scalable manufacturability. So what we mean here is that these components ride predictable experience curves. So unlike a lot of traditional and fuel-based energy sources where prices are determined by volatile global supply and demand shocks, what we see is this ability to scale manufacturing to reach those economies of scale are driving down cost curves and are making these technologies increasingly the lowest cost, fastest option when it comes to new deployment. Third, hardware as software. So once you electrify something, its performance becomes software defined and upgradable. Think about your Tesla. You know, you can get a new software update to your electric vehicle over the cloud, and it can totally change the performance of your vehicle in a manner that simply wasn't possible with previous iterations of vehicle technology. So what we're seeing is investment is up across this electro-industrial stack in the US. Now, you'll notice a couple of key pieces here. Obviously, data centers is the one that's dominating a lot of the conversation at the moment. And here we've seen 1.3x growth from 2020 to 2025. This isn't nearly as spectacular as the rise and more recent fall in electronics manufacturing that we've seen over the same period. And it is worth noting that yes, you know, that we have seen a bit of a dip in electronics manufacturing, which captures both the semiconductors and battery manufacturing that spiked, particularly around that 22 to 24 period. But it still remains well above its kind of 2020, 2021 baseline. And so we expect that, and of course, electric power to continue to be a major source of investment going forward. And what we don't have here, and our colleagues at Rhodium have just or are about to release a fantastic new data set called the Global Clean Investment Monitor that shows how a lot of these investment trends are continuing to get well, they're continuing apace globally. Now, this next slide is the one that really sort of blows my mind each and every time I look at it. Across the electro-industrial stack, so when you look at electricity generation, electricity storage, electric motors, power electronics, and the computing power to ultimately turn all of that hardware into software, you know, what we see are these exponential technological declines. And this simply isn't true in other technologies, and it certainly isn't true in other parts of the energy system. And so well over 90% cost falls across these technologies since 1990. And this fundamentally reshapes the narrative and the global investment landscape. Now, within the US, this growth in investment is simply not spreading evenly, and I would argue nor should it, right? Different regions are going to specialize in different forms of production, different types of economies to drive their development goals. So what we tried to do is put together what we called an electro-industrial readiness index that combines six key ingredients: policy ambition, regulatory certainty, structural economic capacity, physical infrastructure, the actual deployment of these technologies, and the extent to which we're seeing these clusters form or in sort of industrial ecosystems that we know are so critical to being internationally competitive in these fields. And so the results of those that index is shown on the left-hand readiness map, where you start to see some interesting kind of candidates emerge. Texas, Arizona have been clear frontrunners. Nevada as well, of course, with its battery storage manufacturing prowess. Georgia, more recently with solar and electric vehicle manufacturing. And you know what we find when we look through these results is a real diversity, obviously, of how states are sort of playing in this space, and and I think it helps us kind of identify the next steps and where to sort of target actions going forward. Now, as I mentioned, these clusters I think are kind of the real key here. Like state level results are interesting because they look nice on a map, but ultimately it's going to be these industrial ecosystems where you have the shared workforce, the infrastructure, the sites, and the power availability to turn intention into action. And we're starting to see these clusters really develop. So here on the left is a map that includes a bunch of the technologies that we think about in this electro-industrial stack, everything from batteries, data centers, drones, solar and storage. And you start to see some of these clusters emerge. When we combine all of those into this clustered index, on the right-hand side, you see where those leading economic areas or clusters are. And so places like Phoenix, Arizona, which I've mentioned, Bloomington, Indiana, Austin, Texas, Newark, Ohio. These are all areas of the country that are really standing out for their ability to deploy these technologies to generate the right conditions to frankly meet this moment. Of course, at the federal level, we've started to see less support. Obviously, the One Big Beautiful Bill Act removed some of the incentives that allowed, particularly for clean electricity generation, to accelerate at the rate it had. Also, a number of changes that have affected manufacturing investment have led to an acceleration in cancellations of announcements, and you see that on the right-hand slide here as well. Now, so what this means for us is that states need to play the key role in filling these federal policy retreats, and this is a trend that we've seen before, right? The federal government gets excited about something, a new administration comes in, they're no longer excited about it, and it's up to the states to really make good on those promises. And in this left-hand table, what you do see is a number of states really stepping up. So we looked through every state's economic development plans and identified those states that have really put forward proactive proposals and solutions with regards to these electro-industrial technologies. And obvious ones like Arizona and New York in semiconductors, solar and storage in places like Texas and California. But where the rubber really hits the road, right, is in the spending of these economic development incentives. And what you see on the right is that states have really put their money where their mouth is in attracting, in retaining these investments, in turning local economies into these internationally competitive industrial ecosystems that I keep referring to. And so here at RMI, what we've been thinking about is, okay, we have these three pivots. We have a sort of direction set in terms of the technologies, in terms of the geographies that are really taking the lead, and in terms of the types of policies that we need to be doubling down on. But how do we do this in a best practice capacity? So this is why we developed the Greece methodology for evaluating policies. We have these six criteria for what makes best practice industrial strategies, from governance, targeting the right regions, being expansive in your ambition, obviously, focusing on specific sectors and their risks, and ultimately including environmental co-benefits as well. So with that, hopefully that's enough scene setting and context setting for us to understand the technological, geographic, and policy environment that we're operating in. And so with all of that being said, what we wanted to do was turn to our friends at Rhodium that have, just this unbelievable ability to model these results, to think about where these trends could be headed once we adjust those dials somewhat. And so I'm going to turn to Ben to go through those results. And then, as I say, leave time at the end for further questions. Thanks.
Awesome. Well, thanks very much, Lachlan, for walking us through that and for that very kind introduction. Very excited to be here with y'all today to share the results of this work. Just a quick word, Rhodium Group, if you don't know us, we're an independent research provider. We try to use policy expertise and data to come up with some answers that are hopefully useful for folks. And we were very excited to partner on this project with Nice to try to really bring some numbers to the environment that Lachlan has set forth in his remarks, and just sort of demonstrate what states can achieve with well-designed, ambitious policies. So with that in mind, I'll spend a few minutes just setting the scene a little more closely for the work that we've done here, specifically focusing on electro-industrial growth in the Southeast. And then I'll turn to a few of my colleagues. Hannah Collis is going to talk through the energy system outcomes that we see from these policies. And then Galen Bauer is going to talk through the resulting economic impacts of those as well. And as Lachlan said, we'll hope to leave plenty of time at the end for good questions. Hopefully, this is the beginning of a conversation, not the end. So, I think Lachlan did a great job of setting forth what we think about when we talk about the electro-industrial era or electro-industrial growth. And one of the key impacts of this shift, of this transition to electro-industrial growth, is the shift in electricity demand. Um, After decades of flat to very sort of like middling growth, we're now seeing a structural shift in electricity demand. In 2025 alone, electricity demand economy-wide was up nearly 2.5% year on year. And that's not just a blip. That's, we think, an indicator of what's to come rather than a one-off. In our taking stock modeling, which is an annual report that we put out that assesses the US energy system under current policy, we see that total electricity demand could grow by somewhere between 1.5 and a little under 2% each year between now and 2040 on average. A lot of this growth in this year's taking stock report, which does incorporate the impacts of the OBBBA as well as other regulatory changes made at the federal level, a lot of this growth is now heavily concentrated in large loads. So think here especially about AI data centers, new domestic manufacturing for electric intensive processes in particular. Um, it doesn't necessarily mean that that's the only place or the most important place for this demand to be coming from. That's what we see on the horizon right now. But the idea behind the electro-industrial growth is that we're going to be facing sustained electricity demand increases for the foreseeable future. And we really need a grid that's able to accommodate that. And right now, we're not facing that because after, again, a few decades with little incentive for the grid to meaningfully expand or make the investments that are needed, we're now in a crunch time. We're facing lengthy interconnection queues for projects that are trying to come online, trying to plug into the grid. We're facing crunches on things like the availability of gas turbines. And when you have, it's like Econ 101, right? When you've got sustained growth, so increasing demand for electricity meeting constrained supply, the result is what we're seeing today, which is higher prices for consumers and the potential for increasing reliability challenges as well. These dynamics face further uncertainty in light of federal policy changes that have been made over the past year. Lachlan alluded to this already, but the OBBBA tax credit changes result in somewhat different economics for solar and wind and storage and other clean resources. And these are resources that have contributed more than 75% of new capacity on the grid over since 2020. And looking at the pipeline for what's to come, it's a robust pipeline of these same resources as well. So when we think about the need to meet this electricity demand growth, and when you've got people like AI developers who are looking first and foremost for speed to power, you really do want to think about ensuring that you're bringing stuff that can meet that need and come online quickly, and stuff that's already in the pipeline effectively. So, this shift in federal policy, along with the this sort of like shift to electro-industrial growth, we think provides an opportunity for states to capture the lead in meeting this load growth, but to do so in a way that greatly benefits their local economies. By supporting the full stack of electro-industrial technologies, from manufacturing of key components all the way through to deployment of these technologies on the grid and keeping them up and running, states can build robust and resilient economies that sort of meet the moment that we're facing right now. This is the first bit of work that we're doing with Nice on this idea of electro-industrial growth. And for the first cluster that we're working on, we opted to take a look at the Southeast. There's a couple good reasons why the Southeast is a really great place to be focused on to start to establish what states can be looking at as ambitious policy to help meet the need that they're facing right now. First, the Southeast is home to a meaningful concentration of national load growth. More than 30% of total national projected load growth that we see on the horizon between today and 2035 is concentrated in the the 7 states that are in our study region here, which runs from Virginia down to Georgia and Alabama up to Kentucky. This is no surprise to probably most folks on the call, but this area is home to, in Virginia, for instance, so-called data center alley, a major source of data center demand increases for electricity. The battery belt sort of terminates down here in the Southeast with major electric intensive battery processing plants in the Carolinas, in Tennessee and Kentucky. And this is a region that, in addition to those sources of large load, are also just facing sort of like sustained population growth, housing expansion, which contribute to baseline demand growth across the region as well. Second, the region is not starting from zero when it comes to clean investment momentum. In fact, in addition to those major battery factories that I just talked about, we've taken a number of other manufacturing facilities, including solar manufacturing and zero-emitting vehicle manufacturing data from the Clean Investment Monitor, which we're lucky to have to develop here at Rhodium Group in partnership with the MIT Center for Energy and Environmental Policy Research. 44% of total clean energy manufacturing in the United States from 2022 through Q3 of last year occurred in these 7 states. Nearly half of that investment nationwide was contained in these states. So this just creates a foundation for further scaling of these industries. Third, we're already building in a region that has a strong industrial base. The region has deep capacity on auto manufacturing, aerospace, defense, and beyond. This is important for a couple of reasons. First, it provides a large and experienced labor pool for other manufacturing facilities to draw on. And second, maybe equally as importantly, these incumbent industries themselves depend on reliable, low-cost electricity. So to sustain both growth in clean manufacturing, but also this robust industrial base that already exists in the Southeast, low-cost electricity is key. And then finally, Lachlan ran through the Electrotech readiness ratings, and 6 of 7 states are at high or ready or very ready to meet the moment here for electro-industrial investment. So what policies can help Southeastern states take advantage of this opportunity? We model 2 different policy scenarios, and we'll talk about the results of these modeling efforts in the slides that follow. The first is what we're calling our state action scenario. This provides a foundational set of clean electricity and manufacturing tax incentives. And then to see what else is possible, we model an enhanced state action scenario, which pluses up some of these baseline policies, and then also enhances the policies with other things that can help really attract investment, attract manufacturing capacity. You'll note we're focused here on a clean electricity tax credit, a clean manufacturing tax credit. We're focused on these clean technologies for a couple of reasons. First, as I mentioned a couple slides ago, these are the technologies that have made up the lion's share of grid additions since 2020, and also a majority of what's in the pipeline. Sustained support for these investments for these technologies can ensure that we keep that pipeline flowing with robust speed to power for the electricity demand that we need. Critical for attracting and sustaining growth in this region. Second, in the case of both existing and new fossil assets, when you think about building a gas plant, building a coal plant, something like that, you're making an investment for building the thing in the region, but you're sending at least some of your money, usually outside of the region, to buy the fuels for these technologies. That's not the case when it comes to clean stuff, particularly if you're doing the manufacturing of the solar panels, the batteries, et cetera, in the region. You're keeping more of that investment capital in the region, so that you're doubling down on the value of the policies that you're incenting here. Um, so we are taking sort of like a two-handed approach here. On the one hand, on the deployment side, we're trying to support deployment of these clean technologies through clean electricity production or investment tax credit that phases out once any given technology meets a certain level of deployment on the grid. In some cases, we're enhancing those with some additional bonus credits. And we're pairing that sort of demand side pull with the supply side push of the manufacturing tax credits, which essentially provide an incentive for each widget that comes out of a factory that meets criteria within the region. Taken together, these sort of demand side, demand pull and supply push efforts can be really successful, and we've seen the evidence of that in the response after passage of the bipartisan infrastructure bill, the Inflation Reduction Act, the CHIPS and Science Act. Taken together, this was a whole basket of supply and demand side policies. And as Lachlan illustrated, and as we zoomed into in the Southeast, that resulted in both meaningful demand side deployment of this stuff as well as manufacturing. Lastly, just a couple modeling nitty-gritty things before we turn to the results. To estimate the impacts of these policies, we use our flagship energy system model, RHG NEMS, which is an economy-wide energy system model. We pair that with the imply input-output model to translate those system changes in the energy system to the economic impacts that we'll examine. Our analysis here is focused on the years 2026 through 2035. So a 10-year window to demonstrate what's possible here, in this sort of near to medium term, as opposed to thinking about, some sort of 2050 far out goal. And then we look at the impacts of these policies on the region. This makes it easy to understand what's possible here. Each state is going to have a slightly different mix of resources, natural resources, industrial base, et cetera. And so, any given state would want to tailor this to some extent to ensure that it's reflecting, what is best for that state, obviously in consultation with in-state stakeholders and the like. But this is meant to sort of like throw something up in the air and let folks see what could be possible with ambitious, well-designed, well-targeted policy interventions. So with that, I'm going to turn to my colleague Hannah Colas, who's going to talk us through the energy system results.
Thanks, Ben. So like Ben just said, I'm going to cover the major energy system impacts to the Southeast resulting from these two state policy scenarios, starting with capacity expansion. State level electro industrial investment policy increases Southeast grid capacity dramatically, with installed capacity increasing by 52 to 75% in 2035 compared to today's levels. The bulk of this growth comes from solar capacity, which increases above our current policy baseline by about 60 to 90 gigawatts in 2035 with state policies in place. Solar emerging here as a winner here makes a lot of sense given the abundant, high-quality solar resources available in the Southeast, on top of the relatively cheap cost of solar. Other clean generating technologies see smaller deployment gains with enhanced state action. Wind deployment increases by 7 gigawatts, roughly maxing out the available high-quality wind resources in the Southeast. Storage capacity also increases by 7 gigawatts, responding both to tax credits and cheaper cost of capital, as well as the need to balance growing variable renewable generation. Neither policy scenario sees new nuclear capacity, which remains too expensive to compete with cheap solar. All of this new clean capacity displaces existing fossil capacity and prevents some new fossil capacity from getting built. With state policy in place, coal retirements increased by 3 to 7 gigawatts in 2035 compared to our current policy baseline. And we also see 6 to 7 fewer gigawatts of natural gas combined cycle additions through 2035. At the same time, growing variable renewable penetration drives 4 to 5 gigawatts of additional natural gas combustion turbine capacity, which deploys in order to provide extra grid reliability. Next slide, please. In our modeling, we see electricity demand in the Southeast grow by 17% from today to 2035. The growth in new clean capacity spurred by state policy helps the Southeast meet this demand while also driving higher levels of zero-emitting generation in the Southeast. With state-level clean investment policy in place, zero-emitting generation accounts for 58 to 67% of total generation in the region by 2035. That's up from 45% in our baseline and 45% today. As you might expect from the previous slide, most of this growth comes from solar generation, whose shares rise by 5 to 6 times their current levels in 2035 with state incentives. In response to increasing solar and wind, coal and natural gas generation shares both decline compared to current policy. In fact, while gas generation shares grow through 2035 under current policy, they shrink by 8 to 14 percentage points with state policy in place. Next slide, please. And beyond helping the Southeast meet increasing demand, policy-driven growth in clean capacity also reduces the Southeast's reliance on electricity that's imported from neighboring regions. Under current policy, the Southeast meets growing demand by increasing its in-region generation, but also by importing more electricity and exporting a little less of its own electricity. State-level clean investment policy boosts the economics of clean capacity development in the Southeast relative to other regions, changing these trade dynamics. State policy incentivizes energy developers to build more new capacity in the Southeast over other regions, and in-region generation consequently increases beyond the current policy baseline. That extra generation reduces electricity imports and, in the enhanced state action scenario, even transforms the Southeast into a net exporter of electricity to other regions. In other words, this means that there could be spare in-region capacity available to serve new sources of electricity demand that our modeling doesn't currently anticipate. The Southeast clean capacity expansion also helps moderate regional electricity price increases. In our modeling, industrial electricity prices rise by 9 to 11% nationally in 2035 compared to 2025. State-level clean investment policy holds industrial rate increases in the Southeast at just 8% over 2025 levels. So in addition to the spare capacity that we just talked about, these relatively lower electricity rates could create a favorable environment for attracting new investment in electricity-intensive industries that rely on low cost and reliable power. The impact of state policy on prices also extends beyond the industrial sector. Across all sectors, Southeast electricity prices decreased by 1 to 2% in 2035 compared to current policy. And while this is a relatively small change, it saves residential customers more than $1 billion through 2035, and it represents a small amount of economic relief against a backdrop of nationally rising electricity prices. And finally, state-level clean investment policies benefit the climate as well as the energy system. Even as in-region generation increases, Southeast power sector emissions decline by about 60 to 80 million metric tons of CO2 in 2035 compared to baseline. That's a 21 to 36% reduction in power emissions. Now I'll turn it over to Galen to walk us through the economic impacts of these state policy scenarios.
Awesome. Thanks so much, Hannah. So policies supporting electro-industrial expansion in the Southeast generate tangible economic opportunities across the region. The 4 categories of economic impacts we explore are private investment, net employment effects, occupational opportunities, and net fiscal impacts. Next slide. These state policies spur significant private sector investment into the region. Over the 10-year window, the state action scenario results in $46 billion in additional private capital investment compared to current policy. And in the enhanced state action scenario, this would attract $81 billion in private investment into these states. These figures reflect only private capital investment, so the upfront capital needed to develop and build these projects. It does not include any investment associated with the ongoing operations and maintenance that these facilities need once they're up and running. And it's also net of any government expenditures. And in both policy scenarios, private investment is driven primarily by the build out of additional solar capacity. And then there's slight decreases in investment in natural gas capacity, which are outweighed by increases in investment in solar, wind, and storage. Next slide. Looking at the employment impacts across both policy scenarios, net jobs in the energy sector and associated industries increase substantially compared to current policy. And all of the jobs here reflect job years, which represents one job sustained for 1 year. So as you can see, we break top-level job results out across two different dimensions. First, we classify results as project-level jobs or supply chain jobs. The project-level jobs are associated with direct inputs, so this includes construction, engineering, and operating expenses of electricity generation facilities and the associated transmission and manufacturing build-out. And then the supply chain jobs refers to jobs associated with any economic activity upstream of project-level jobs. Roughly 2/3 of the jobs are project-level jobs, and the remaining 1/3 are supply chain jobs. And then within project level and supply chain jobs, we further disaggregate by project phase. So development jobs are those associated with building energy facilities, and operations and maintenance jobs, O&M jobs, are the jobs to operate and maintain these assets. Since the installation phase of clean energy projects is the most labor intensive and O&M requirements are relatively modest thereafter, around 90% of employment is associated with the development phase. And across these categories in the state action scenario, we find jobs increased by 164,000 to almost 198,000 job years between 2026 and 2035 compared to baseline. In the enhanced state action scenario, it's associated with more than twice as many net jobs, more than 350,000 to 425,000 job years over the same time frame. And it's important to note that these employment numbers are inclusive of any job losses resulting from displaced existing fossil capacity and new fossil capacity that would have otherwise been built in the baseline scenario. Next slide, please. Okay, so in both state action policy scenarios, examining employment impacts separated by technology largely mirrors the energy system capacity changes relative to baseline that Hannah showed earlier. So the solar industry is really the industry with by far the largest increase in jobs, accounting for about 70% of total job years on an absolute basis. And in both state action policy scenarios, we also see increases in jobs associated with solar manufacturing, wind energy, storage, natural gas combustion turbines, and transmission, which are all industries with additional capacity and build out compared to baseline. And then we also see net negative jobs associated with building and operating natural gas combined cycle plants, given the decrease in capacity compared to baseline, as well as a decrease in coal O&M jobs, which stems from a decrease in coal generation under the state action scenarios. Next slide, please. So to better understand how employment impacts translate into workforce needs, we explored net changes in occupations between the state action scenarios and baseline. Among both development and O&M jobs, we found exclusively net increases across all occupational categories. The significant growth in roles, particularly those related to solar expansion and solar manufacturing, more than offset any occupational losses tied to declines in other technologies. So the results here are showed for the enhanced state action scenario. However, the state action scenario results only had minor distributional differences. So pretty much the same. So for development occupations, the top occupations include construction and installation workers, which include solar PV installers and electricians, financial operations and metal workers and assemblers. And then the top O&M occupations include construction trades workers, executives in business operations, and sales representatives. These results primarily reflect the large number of ongoing O&M occupations generated by the increase in solar deployment and solar manufacturing. Next slide, please. So we also examined government fiscal impacts over this 10-year period. Regional investments into electro-industrial growth increased state government revenue collections from a variety of sources, including personal taxes, corporate profit taxes, and taxes on production and imports. The state action scenario would generate almost $900 million in gross increase of revenue, while the enhanced state action scenario would result in $1.9 billion in additional tax revenue between 2026 and 2035. However, these policies also come at a cost, but to put the outlays into context, they are still relatively small relative to state budgets in this region. So the annualized net fiscal impacts of these policies is $468 million in the state action scenario, which is only 0.3% of these states' current cumulative budget. And it's 3.1 billion in the enhanced state action scenario, which represents 1.9% of these states' budgets. And then lastly, government spending on clean energy tax credits mobilizes private capital at a scale that far exceeds the public cost. So in the state action and enhanced state action scenarios, every $1 of public investment yields $8.16 and $2.48 in private investment, respectively. So with that, I will pass it back to Ben for some key takeaways.
Awesome. Thanks very much, Galen. Thanks, Galen and Hannah, for walking through those results. So hopefully this gives you at least a little bit of a teaser for what we've got going on in this report. I encourage you to take a closer look. It's on our website, and I think probably on NISA's website as well. In general, though, we find that, in this new electro-industrial era, states can be well positioned to capture policy leadership and really drive meaningful private investment and jobs while also building out the robust grid that we need. And we've walked through these already, but just to mention, that includes more capacity on the grid, more clean manufacturing in the region, and that in turn yields tens of billions in private sector capital crowded in and a robust increase in regional jobs as well. So we'll leave it there, I think, and there's been some really good questions flowing in already, so looking forward to hearing from having a good conversation around these questions.
Great. Thank you so much. A lot for us to dig into there. I thought RMI brought the charts, but Rhodium really stepped up its game. So thank you for that. As Ben said, we've had a couple of great questions in the chat. I'm going to take a little bit of moderator's privilege here and ask what I'm interested in as well. So just to start with, I mean, when I went through these results, there were a couple of things that really stood out to me and surprised me. I think one of which is, there was a lot of talk about industrial policy at the national level, that it was too expensive, it was blowing holes in budgets. And I was surprised that these policies came in at the sort of expenditure they did. They were sort of cheaper than I anticipated. But a more general question for the three of you, what surprised you in these results? One of the great things about a modeling exercise like this is it hopefully pulls away some of our priors, some of our sort of subjective, views on some of these things, and we get to think about it a little more objectively. So what surprised you when you crunched the numbers and saw the end results?
Yeah, I mean, I think what you've touched on one of the key things, which is the relative cost of these interventions, and it really does speak to some of the inherent resources that the region has, particularly in thinking about the expansion of solar and storage. Here we're working with a really it's a sunny part of the country. I'm from just outside the region, the Florida, the Sunshine State, but I can attest that the solar insulation is quite excellent in many regions in many parts of this region. And the result of that is that you can get fairly robust responses from relatively modest policy incentives. So to put the size of the tax credits into context, these are between a third and maybe half the size of what was being offered at the federal level. So it really does just speak to the value there. And then the other thing that was interesting to me is just seeing the extent to which this results not only in the ability for the Southeast to meet its own electricity demand needs, but also to become sort of an exporter, a powerhouse, if you will, for neighbors as well. Taking advantage of some of the inherent advantages that we've already talked about, and either helping to ensure that their neighbors are getting power, or again setting up the environment that can attract even more growth beyond. Galen, Hannah, anything else that y'all wanna layer on there?
Yeah, so one thing that also surprised me, this was my first time doing an economic impact analysis where we were looking at net impacts and looking at any job losses from displaced fossil capacity. And I really didn't know how that was going to look when it came to economic impacts and occupational and employment impacts. And it was really cool to see just how positive all of the impacts were ultimately, even taking into account any job losses in certain industries. Just overwhelmingly, this is good for the economy in the Southeast.
I'll just echo quickly exactly what Ben said. The pretty dramatic change to electricity trade dynamics in both of our policy scenarios was something that I was not expecting at all. It just shows how effective these kinds of policies can be.
Yeah, no, I completely agree, and I would love to dive into the details of the policies and which ones we chose and how we got there. But I will take one from the audience before I dive too much into my own interests. We have a question here about how the model calibrated for projected data center announcements, and a little bit also about which capacity expansion model we used. And we've got a good wonky crowd, I see, which is great
Love to see you. Love to see a fellow
Yeah.
modeling nerd in the chat. That's great. So we have exogenous projections that we updated as of July of 2025 for data center projections. We do this as part of our taking stock report every year. So there's certainly been developments over the past 6 or so months since then that will reflect when we take this report back up now. But it still provides a reasonably decent sense for the expected growth in data center demand that's already on the horizon, that was on the horizon as of that time. And then let's see, sorry, I lost the quote. There it is. We use NEMS, the National Energy Modeling System, which is the same tool that the Energy Information Administration uses to produce their flagship annual energy outlooks and other policy analyses. So there's a capacity expansion model that's embedded as part of that, which incorporates to the question limits on the ability for instance, the gas turbine constraint, limits on meaningful addition of gas turbines while we're still in this crunch environment, limits on transmission capacity between regions and pieces like that. So as well as construction times for individual generators. So we try to do a good faith representation of how the actual energy system works. It's all down to how good you can do that on a spreadsheet. There's obviously stuff that's outside of the realm of the possible there, but it's a reasonably good estimate for this, I think.
That's great. Thank you. So we have a question from Steve in the chat about Ohio policymakers taking a look, and so it is worth thinking about. We decided to focus on the Southeast because we have seen this clustering of electro-industrial, particularly manufacturing investment, but increasingly generation deployment as well. But one thing we wanted to do was think about tools that aren't necessarily specific to a region, and pick a region that was representative, and pick policies that were illustrative for other regions to learn from. So wondering if you could sort of speak a little bit to how can other states, how can other regions sort of extrapolate from these results? How relevant are these results to other parts of the country when looking through this report?
Yeah, I mean, I'd say one of the key things that we took away from this is that it's really critical to play to your strengths. So in Ohio, that may not be the same thing that it is in Georgia, right? And so a tailored set of policies is really important to pull that in. However, at the same time, again, with the sort of step back that the federal government is taking, we think that there's likely reasonably low cost policy steps that any state could take to position themselves well to succeed in this sort of like an electro-industrial era that we're turning into. Certainly, in Ohio, there's data center demand growth, not like Virginia, but still, like it's been a center over the past few years. Likewise, a major both historical and current center of manufacturing strength, right? And so again, thinking about what the resources that you're bringing to bear are in a given region, so that you can take advantage of those resources, build on them, in a reasonably efficient manner.
Great. Yeah, thank you. And I totally agree with that. And just to sort of preview, we are doing another one of these exercises in the coming months for the sort of South Central, Southwest region. We're going to be looking particularly at enhanced geothermal, at advanced nuclear, at some of these so-called kind of clean firm options. And so just to preview, we're going to be thinking about this question similarly, but also slightly differently for other regions. As you say, Ben, how can different regions play to their strengths when it comes to their natural endowments, to their workforce, to the economic sort of structures that they're blessed with? I wanted to speak a little bit about the policies that went into the model. Obviously, there's a lot of choices that need to take place before the model can then spit out its results. So, just wondering, how do we choose these particular policies versus others? And in particular, I think a lot of people will recognize some of these policies from the federal government experiences, as you say. What were the differences between what we modeled and what happened at the federal level? So I know it wasn't just the overall size of the tax credits, but we had different phase outs, for example. If you could just speak a
Yeah.
little bit to our thinking in moving from and maybe learning from some of the lessons that were perhaps hardly we like to think we learn from our mistakes, right? And
Yes.
so which ones of those learnings did we apply in this exercise?
Um, so I think two things there, and would welcome Galen or Hannah to jump in once I make a couple comments here. One is yes, learn from what didn't work, but also learn from what did work. And we saw a really robust response to the so-called 45X clean manufacturing production tax credits that were stood up as part of the sort of policy environment that we were recently in, and have sort of walked back from to some extent. And so like let's learn from the response that we saw there, and we directly incorporate the sort of response into our modeling of what we think these policies would do. So one thing is like let's take advantage of what we know works there. The other thing is it's really critical when you're designing these policies to size them appropriately so that uh, you know uh, uh, a reason that the tax credits that were modified substantially in the OB3 context is because of their price tag. And we know that state governments face even greater fiscal pressures than the national government does. So sizing these policies in a way that's responsible to those state budget levels, and that is frankly reasonable from a fiscal and political perspective, is important as well. And then maybe one third thing is just understanding what the enhancements are. So, we looked at those like, core policies, but then we have some things like we've seen a really robust market develop for transferable tax credits. So this is the notion that, if you don't have the appetite as a renewable developer or something to absorb the tax credit yourself, you can partner with somebody who does and benefit from the incentive without having to monetize the tax credit yourself. Um, Ensuring that the policies are designed in a way that can draw on that sort of framework as well is another thing that's been really critical from our research on what worked and what didn't work from in the IRA context. Let me pause again, or Hannah, anything else that y'all want to add there? Okay, great.
Right. We have one more question in the chat that I'd like to bring up. And Thomas asks the degree to which solar sort of dominates this whole analysis. And as you say, part of that obviously is the strength of the resources in the region. But solar is can be a volatile market, and so just wondering what sensitivities there might be in thinking through the future of solar over the next kind of 5 to 10 years, whether that's technical, trade, legal variables, and how that might affect the results that we've seen come out of your model.
Sure. Yeah, it's a great question. We should be clear. We modeled these scenarios using sort of like a central case, where we expect solar prices to achieve a certain level. We likewise assume natural gas prices will be at a certain level in the future, wind prices, nuclear prices, et cetera. So that's all interconnected, right? In a world in which there's, for instance, continued trade barriers to solar, that could put upward pressure on relative to the prices that we have now. We incorporate some tariffs already. It's always a moving target to try to figure out what the latest tariffs are. So we've done the best that we can, but there is some sensitivity around how exactly those would flow through. We're also hoping that by incenting more in-region manufacturing, we're mitigating against some of the risk of that of any trade barriers that would come from those tariffs. But if we're on a fundamentally different pathway, either cheaper or more expensive for solar, if we're on a fundamentally different pathway, either cheaper or more expensive for natural gas, that would yield meaningfully different outcomes here. The important thing that it wouldn't do is change the fundamental cost-benefit ratio of this, though. So, the nice thing about the approach that we've taken is you're only paying for what you get, right? You're not writing a blank check. You're saying you deliver clean electrons to the grid, you deliver, solar cells that you've manufactured in this region, and we'll give you an incentive to do that. If you don't deliver on that, then you don't get that incentive. That's a really important insurance policy, so to say, to ensure that if these results don't bear out, if the impact is not quite as robust as we've seen, you're still not on the hook as a state government for covering expenses that you're not getting benefit from.
Yeah, it's a great point. I think it's a really good argument for why the tax code can be a really powerful policy tool, right? Often in the economic development world, it can be a series of tax credits or grants or subsidies that then require these complicated clawback provisions, right? Oh, you're going to create this many jobs, or you're going to produce this much of widget X, Y, and Z. But if you don't, then we have to go through a process of clawing that back, which, there are a couple of projects across the country right now going through that process, and it can be quite difficult. So Look, I just wanted to thank you all so much for your time. I want to thank the participants that stuck around through what was a wonky discussion, but I hope really set the tone for what we're trying to do at RMI at the Knee Center and in collaboration with the Rhodium Group, which is think really hard about okay, this opportunity is out there. Let's go get it, but let's get it in a way that effectively brings in as much of the private sector as we can and spends taxpayer dollars as efficiently as we can. Right? We don't want to waste that money, waste people's sort of hard-earned cash. Because particularly at the state level, where every dollar spent on an economic development incentive or a production tax credit is a dollar that could go to a local school or a hospital, and we want to make sure those dollars are spent, as effectively as they can be. So we have a bunch of research products coming out over the next couple of months. Our work with Rhodium is really focused on this key bottleneck that we think about in terms of the power market, in terms of getting enough electricity on the grid to meet, this huge surge in demand. We have upcoming work with the Upjohn Institute for Employment Research, particularly focused on manufacturing projects and the use of economic development incentives. So keep an eye out on this space, and thank you again for joining us, and we look forward to seeing you next time. Thanks.